Hello everyone and welcome back. My name is Mr. Kovalt, and in this video we're going to talk about trends of the periodic table. So let's get into this. So the first thing we want to talk about is atomic radius. So what is the atomic radius? Well, and anytime you're talking about radius, you're talking about like the distance from the center of a circle or sphere to the outer boundary. And so here you can see this is the atomic radius. And here you have two hydrogen atoms that would be bonded together. And so what we mean by atomic radius is this part here. So the radius of a particular hydrogen atom. So what is a radius? Well, here we have the atom, and we have the nucleus in the center, and we have the electron cloud. And so we are measuring from the nucleus to the outer boundary of the electron cloud, and that's our radius r. And so that's what we kind of mean by that. Ideally, we would measure again from the nucleus to the edge of the last filled orbital or valence orbital. And then we would be able to get that. However, we can't do that. Orbitals are just estimations of where electrons might be, so there's no definitive end or edge of an orbital. So the edge is fuzzy. And so what we do is we just measure half the distance between two identical atoms bonded together. And so when we can find how big a bond is, or how big the hydrogen molecule is, and we can know this distance, and then we just, since it's the same atom, then we just divide this distance in half, and we get the radius of a hydrogen atom from that. So what's the pattern or trend in the periodic table when we're talking about atomic radius or size? So let's look at a few elements. So if you have your periodic table, we're looking at the elements hydrogen, lithium, and potassium, and you'll notice they're in the same group, group number 1. And here are their atomic numbers. So atomic number 1, 3, and 19 going down the group. And here are their atomic radii. So the atomic radius of hydrogen is 0.37, the lithium is 1.23, and potassium is 2.03. So then the question is, how does the atomic radius increase? Is it increasing from top to bottom, or is it increasing from bottom to top? And as you can see, hydrogen is on top, and lithium is the second one, and potassium is the fourth one. So as we go down a group, you'll notice that the atomic radius increases. So the answer is that atomic radius increases going down a group. And this is true for any of the groups that we look at. Now, if we look at elements in the same period, so if you look at sodium, potassium, and chlorine, those are all in period 3. So then the question here is the atomic radius increasing left to right, or is it increasing right to left? So here we can see sodium is the most left in that period, and it has an atomic radius of 1.57. And then chlorine is the most to the right in that period, and it's got 0.99, and phosphorus is in between. So right away we can see as you go from left to right, the atomic radius is decreasing. So that means going from right to left, the radius is increasing. And so those are the trends that we're seeing. And so top to bottom, increasing, right to left, increasing. So here's what it looks like on the periodic table. So again, you could see that the sizes of the atoms as you go from right to left, this size is increasing. So as you go right to left in any group, you'll notice that the size increases. And you could see that if you go down a group, size increases as well. So going down a group, size increases. Going from right to left, size increases. So if we look at the overall general trend of the periodic table, atomic radius is is increasing from the top right down to the bottom left corner. And so that's the trend of atomic radius. So these are trends you're going to need to know. So the question is then, why does atomic radius change in this manner? What's the reason behind this trend? So the first part we need to talk about is when we're increasing down a group. Um, what's happening when we go down a group? When you go down a group, you're adding more energy levels. So remember the period number. If we go back to our periodic table, the period number here on the left indicates the number of energy levels you have in your atom. So how many energy shells or quote unquote orbits will you have in your atom? And that number of shells corresponds to the number of the period number that you're in. And so as you can see, as you go down a period, you're increasing by one. So that means you're adding one shell every time you go down the period. So this potassium has uh, four energy levels or four energy shells around the central atom, around the nucleus. And and if you go down to rubidium, that's in period 5, so it has 5 electron shells and so on. And so if you add a shell, that's like adding layers to an onion. The more layers you have, the bigger your onion. So the more energy levels you add, the bigger your atom. So you're adding more energy levels. So what happens when you add more energy levels? Well, the inside electrons are shielding the outside electrons from the nucleus. So you can kind of think of the negative charge of the inside core electrons is kind of canceling out some of the protons in the nucleus. So you could think of it as a one-to-one. Every one electron on the inside is canceling out some of the charge in the nucleus. So it's a one-to-one, but not quite. But you could think of it as a one-to-one. So the nucleus isn't able to act as strongly on the outside valence electrons. So in this picture, you could see the valence electrons are here, and then here's the nucleus, the protons in the nucleus. And to think about it this way, um, the positive protons in the nucleus are attracting the negative electrons. Um, but you can see that the core electrons on the inside that are closer to the nucleus are able to shield or cancel out some of that charge of the nucleus. And so what ends up happening is that the valence electrons here on the outside don't feel as great of a force on them by the protons in the nucleus because the core electrons are um, canceling out some of that charge and therefore reducing that what is called the effective nuclear charge on the electrons. So the electrons just don't feel as big of a pull as they should because of the shielding due to those inner electrons. Okay, so again, the inner electrons we're referring to here are just the electrons that are not valence electrons. The valence electrons are the outermost shell. Then all the other electrons that are on the inner shells are called core electrons, and therefore they shield or block the attractive force of the nucleus. Um, so the nucleus is not able to pull in the outside electrons, as closely. Um, so therefore, you're going to have a bigger radius. Um, this is what happens when you're going down or going across a group here, or going across the period. Um, so as you're going down the group, here we're talking about going down a group. What you're doing is you're adding a new shell every time you go down and as you go down a group, as you go from one period to the next in the same group, you're adding another shell. And then because you're adding another shell, the valence shell is getting farther from the nucleus, and so that distance from the nucleus is getting bigger, and so therefore the atoms get bigger. So as you go down a group, the atoms get bigger because you're adding shells, and the valence electrons are not able to be pulled in as strongly. So what about across a period? What's happening when you go across a period? Well, when you go across a period left to right, remember the atoms or the elements are ordered according to atomic number. And so as you go across a period, the atomic number increases by 1, which means that you are adding 1 proton to the nucleus as you go across the table. And what happens when you add another proton, another positive charge to the nucleus? Well, that nucleus is going to have a greater positive charge. And so those electrons are going to feel the pull more strongly because there's more protons doing the pulling. And so those electrons are going to be pulled in closer. So the bigger the nuclear charge, then the closer those electrons will be pulled into the nucleus, because again, the nucleus has a bigger positive charge, and therefore it's going to pull in uh, those those electrons closer. So the protons have a bigger pull than the electrons do. Adding more protons means that they're gonna the more they can pull electrons, and therefore the smaller the radius. So this means that you have a greater effective nuclear charge. Um, so here, greater effective nuclear charge means you're going to have a smaller radius. The bigger the nuclear charge, the more positive protons you have in your nucleus, the more it's going to pull on those outer electrons, the more it's going to bring them in closer, and the smaller their radius is going to be. All right, let's talk about ionization energy. So that's the trend in um, size. What about ionization energy? So, what is ionization energy? First of all, we need to define it. So, the definition of ionization energy is that the energy that's required to remove one electron from a neutral atom of an element. So, you have an atom, it's neutral, and we want to know, well, how much energy will it take to remove an electron from that element? So, how hard is it to remove an electron? Basically, that's the question being answered by ionization energy. So, the more energy that's required to remove the electron, the harder it's going to be to remove that electron. So, it's going to take more energy. So, you could think of this as related to how strongly those electrons are pulled into the nucleus. So the stronger the pull, the more energy it's going to take to remove that electron. So keep that in mind. So what is this pattern to ionization energy? So again, if we look at our table with the elements, we have going down a group, hydrogen, lithium, potassium, again, you can see that the atomic number is getting bigger as you go down. And then you can see here that ionization energy, as you go down the group, is becoming less. So the question then is, how does ionization energy increase? So here we're looking, if we're going down a group, the ionization energy is decreasing. So that means it's increasing going up the group, and we can see that from the numbers here. So that means from uh, top to bottom, the ionization energy is decreasing, but it's increasing going up the group from bottom to top. And what about going across a period? So lithium, phosphorus, chlorine. What happens to ionization energy as you go across from left to right? And here we can see that as you go from left to right, the amount of ionization energy increases. So what does that tell us? So, in answer to the question, ionization energy increases from bottom to top, so going up your table. And it also increases going from left to right. That's something we want. Okay, so there we're going, we can see the trends. And so now we can go to our periodic table and we can see here that ionization energy increases from left to right, and it increases from bottom to top. So therefore, the general trend of ionization energy is going from lowest is at the bottom left corner of the periodic table all the way to the top right corner of the periodic table. So fluorine is the most electronegative, while francium is the least electronegative. I'm sorry, we're talking about ionization energy. So again, the fluorine is going to have the highest ionization energy, and francium is going to have the lowest ionization energy. And again, remember, the ionization energy is the amount of energy it takes to remove the electron from the valence shell and make an ion. Okay, so noble gases are the highest. So noble gases do not want to lose electrons at all. So it would be really hard it would be much harder to get them to lose their electrons. So they're very unreactive. So why do we see these trends? So ionization energy, so we said it increases left to right. So why is this? So why part one? So we have a smaller radius, and so the greater the effective nuclear charge. So there's a greater effective nuclear charge. The nucleus is holding on to the electrons tighter, and so therefore it's harder to take away, right? So um, so we saw before, as you go from left to right, that the effective nuclear charge is getting bigger. There's going to be a stronger attractive force on the electrons. It's holding on them tighter, and so it's going to take more energy to remove the valence electron, right? And so more energy, it means it's going to be a higher ionization energy. So the atom wants a full valence shell. They don't want to give away their electrons if they're almost full. They want more electrons. So to take an electron away from the neutral atom is going to require a lot more energy as you go across from left to right. So what about from bottom to top? Why does ionization energy increase from top to bottom to top? Well, that's because there's less shielding, right? So you've got less shells as you go. Remember, the period number corresponds to the number of energy shells you have, right? So if you're going from the bottom to the top, you're decreasing the number of shells. So that means the electrons are going to be closer to the nucleus, and so they're going to feel a stronger pull again. So the nucleus is going to be stronger because there's less shielding, and also because the electrons, the valence electrons, are closer to that nucleus. And so when the electrons are closer to the nucleus can pull on them more strongly, and therefore it's going to take more energy to remove an valence electron. And so it's harder to take away. So therefore, higher ionization energy. So electronegativity. What is electronegativity? Um, so electronegativity is a measure of the ability of an atom in a chemical compound to attract electrons from another atom in the compound. So basically what we're looking at is how strongly the atom is going to be attracting electrons in a bond. So they're bonded together, and they're sharing these electrons. Well, which atom is going to be pulling on the electrons more? So it's like tug of war. So what's the pattern in electronegativity? So the pattern here is it's going to increase from left to right. So you can see here it's increasing from left to right, and it's going to increase from bottom to top. So the general trend is going to be increasing from the bottom left corner of the table to the top right of the table. So that's the trend of electronegativity. So the most electronegative atom is fluorine, the least is francium. So why does the electronegativity increase in this direction? So when we're talking about increasing left to right, again, when you go from left to right, your radius is getting smaller because of the effective nuclear charge. Your nucleus, as you go from left to right in the periodic table, is getting more positive. You're adding more protons. There's more protons, therefore there's a greater positive charge, and therefore it's pulling on those electrons more. So this is going to create a smaller radius. So then again, the nucleus is pulling harder on the another atom's electron. So in a bond, if you've got uh, one atom that's more electronegative, its effective nuclear charge is greater, so it's pulling on those electrons in the bond more than the other atom. So uh, atoms are closer to filling their valence shell. So they really want more electrons. So the more electronegative atoms are on the right side of the table. Those atoms on the right side of the table are closer to getting their energy level filled, and so they really want to pull on those electrons. They want to have those electrons. And so that's why their electronegativity is greater. As you go from bottom to top, as you go up a group, why does electronegativity increase? Well, again, because your your radius is getting smaller when you go up the group, right? So again, your the number of shells you have as you go up a group get less. So that means the valence electrons are closer to the nucleus. There's less shielding, so you have less electrons, inner core electrons, therefore less shielding, and therefore the electrons are feeling a stronger pull. And so the nucleus can pull harder on those electrons, and therefore that's a sign of a higher electronegativity, that stronger pull on the electrons. So what about reactivity? So what is reactivity? Reactivity describes the type and size of the reaction. What does it react with? Is it big or is it a small reaction? But the magnitude changes, right? So elements are in the same group, right? Elements in the same group have similar behaviors. Why do they have similar behaviors? It's because they have the same number of valence electrons. So sorry about the slide here, the electrons, it's overlapping. So elements in the same group have the same valence electrons. So remember, the group number tells you the number of valence electrons for the representative groups, for the main groups. So the 1A, the 2A, 3A, 4A, 5A, 6A, 7A. So those group numbers tell you the number of valence electrons. And therefore, all the elements in the same group have the same valence electrons, and therefore they have similar behaviors, similar properties. But the magnitude of the property is going to change. The magnitude of the reaction is going to change. So elements in the same group are going to undergo the same reactions, but as you go down a group, the magnitude of that reaction is going to be different. It's going to change as you go down a group. So what's the pattern? So it's different based on the class of elements. So metals, the reactivity increases as you go down a group. So the metal side, on the left side, you have the metals. So as you go down a group, the reactivity increases. But for nonmetals that are on the right side of the table, they become more reactive as you go up the group. So metals become more reactive down a group, nonmetals become more reactive up the group. Noble gases are the least reactive, so they don't want electrons. Their electron shell is full, so they don't need to change. They don't want to change. They don't need to lose electrons or gain electrons. They're happy the way they are. So they're going to react hardly at all. So they're not going to react. So here we have the periodic table. And so if we're looking at, say, the alkali metals, they're the most reactive metals. And then the most reactive nonmetals would be the halogens in group 7. So the group 7 are the halogens, most reactive nonmetals, and the alkali metals all the way to the left. Group 1 is going to be the most reactive metals. So here we have the noble gases. These are inert. They do not react. So why do they have these reactivity trends? What's behind the trend? Well, let's talk about reactivity in groups. So the metals, again, we said that they're more reactive as you go down a group. Well, why is this? Well, it's easier to lose electrons. So as you go down the group, the atom gets larger because you're adding another energy level. And so because you're adding another energy level, those electrons are getting farther from the nucleus, and so they're not feeling as great of a pull by the nucleus because they're farther from the nucleus. So there's a larger radius, so it's easier to lose those electrons. There's more shielding, right? There's more core electrons that are kind of shielding the nucleus. That's also part of it. The valence electrons, therefore, they're farther away from the nucleus, and they're not feeling as great of a pull, and therefore there's a lower ionization energy. So if there's a lower ionization energy, then it's easier to remove the electron, and they're going to react more quickly. They're going to be more vigorous. It's going to be a larger reaction. So it's easier because it's easier to take away electrons. So you got a quick, big reaction with as you go down a group. For nonmetals, nonmetals are more reactive as you go up a group, right? So why is that? That's because it's easier to gain electrons. So remember, the nonmetals want to gain electrons. Well, as opposed to the metals want to lose electrons. So with regard to that, that's the difference. So if we're thinking about metals are want to gain electrons, and so therefore it's the easier it is to lose that electron, the more it's going to react. But for nonmetals, they want to gain electrons. So if it's easier to gain, the easier it is to gain an electron, the more likely, the more it's going to react.